Good morning, student. Today's our objective for the first order reactions. We apply the integration method to calculate the rate constant of the first order reactions. In the previous classes, I had given an idea about the average rate, instantaneous rate, order, molecularity, and how we determine the order if the experimental values are given, and how we plot the graph for the zero order reactions and the question based on it. So today, as per your book, the unit is chemical kinetics continued, unit 4. Now our objective, integration method for first order. Consider a reactant that will give the product. So when the time allowed is 0, at time t0, this initial concentration, time allowed 0, this is the initial concentration, and after time t, the concentration of reactant is A. That is, product is formed. So R naught, this is initial concentration of reactant, and R, the concentration of reactant after time t second, right? T second. So the rate we can write minus d R by dt is equal to k, and it is a first order, so this is R. Now arrange it, minus d R by R, this is k into dt. Now integrate it, integrate it. So this is minus d A by R is equal to k, this is dt. So as per formula, dx by x integration is equal to ln x, read as log x, and dx integration is read as x. So this is the formula. So we write here what's that is minus ln R kt plus C or I, right? Or we write I. This is equation 1, where I equal to integration constant. So when time allowed is 0, then R, what is the concentration of the reactant after lapse time t second. Now this R becomes equal to R naught. When t is 0, then this will be the initial concentration of the reactant. So this is R naught. We put the value in 1. Putting in equation 1. So minus ln r naught k t0 plus I. So we get the value of I. Therefore, I is equal to minus ln, this is r naught. Now put the value of I in equation 1. So we can write here ln r is equal to kt, and this is equal to minus, this is equal to minus ln, and this one is r naught, right? So we can write here as, so this is ln minus kt is equal to ln r naught minus ln r naught, this kt is equal to this one ln r, this one. So this can be written as ln r naught by r, this is equal to kt. Now k is written as in the form of to the base 10 2.303 by t and log, and this one is r naught by r, this one. So this is the rate constant for the first order reaction. So if the initial concentration is known and concentration after the lapse of certain time is known and the time is given, we are able to calculate the value of the rate constant, and whatever be the unit of the rate constant, because this is a concentration and concentration, so it will cancel out. So the unit of concentration will be second inverse. This is second, that is time inverse. Simply, if it is time in second, second inverse. If it is in hour, hour inverse. If it is minute, then it is the minute inverse. So this is the one. So there are so many problems based on that equation. So we see the another equation can also be, because some numerical given in your book that will based on that equations. So let us we see. One equation we get so let me see from here. This minus kt is equal to, can be written as ln r. This is the first we write here, minus ln r is equal to kt minus ln r naught. This is from here. So we can write it as minus kt is equal to ln r minus ln r naught, right? For t1 second, this minus k t1 is equal to ln r1 minus ln r naught. Now for t2 second, minus kt This is KT2 ln R2 minus ln R naught. Suppose the equation 3, this is first I have taken it, suppose it is 2 and it is 3. Then 3 minus 2, what we get? 3 minus KT2 minus or minus, that will KT1 is equal to ln R2 minus ln R naught, and this is minus ln R1, and this minus minus plus, so ln R naught here. This is ln R naught. So what we get here, this is a minus KT. So minus K is common, and this is T2 minus T1. We can write it, right? And ln, and this one will cancel, so it can be written as ln R2 by minus ln R1. We can write this equation as. Now this K comes this side, so it can be written as, so this is written as K come this side, it come this side, so this is written as ln, this is R2 by R1, right? R2 and R1, we take in the initial concentration, so we take it in the square bracket or here, where R1 and R2, and here is minus K, and this is T2 minus T1. So K is equal to, this can be written as minus 1 by T2 minus 1 by T1, and there is a negative sign, so again we can write it as ln R1 by R2 due to this negative sign. So this equation can be written as 2.303, and this is T2 minus T1, and this is equal to log, this one is R1 and this is R2, this is K. So on this formula, problem is given in your book, that's why it is needed to derive this formula and how it will comes. Question is given, the initial concentration of your reactant is given. Suppose R1 is given and the initial concentration is given. Initial means the time allowed is 0, and after certain time the concentration of that reactant changes and it comes to be, that is R2 is given, and the time required is certain given, that is suppose 60 seconds is given. So you calculate the rate constant of the reaction. By using that formula, we are able to calculate it. So we note the another formula in the top of the board in order to solve the numerical problems. So I may erase it. So you will see. So one formula, 2.303 by T log R naught by R. This is one. This is another formula, K is equal to 2.303, and this is T2 minus T1, and log, this is R1, here is R1 by R2. What is here R1 and R2? R1 and R2 are the concentration of the reactant at time T1 and at time T2. So we write here, that is R1 and R2. So what we write here, that is R1 and R2 are the concentration of the reactant at time T1 and at time T2. So we have the use of the two equation to solve the numerical. Keeping in mind R naught is the initial concentration and R is the concentration at a given time. And if the two, suppose we take for that example, suppose N2O5 and it will give NO2 plus O2 twice N2. It is a first order equation and the initial concentration is given. Initial concentration is given. Suppose it is X mole per liter, right? And after time, suppose 60 second, the concentration of N2O5 becomes Y second, Y mole per liter. Find the rate constant. And this is the general, find the rate constant. Then how you will solve it? By using that formula, we are able to solve it. Because we write here, that is 2.303 and this is T2. What is T2? That is 60 second and T1 is the initial concentration, right? So we write here that is 60 minus this is T0 log, and what is the initial concentration, that is X, and what the after this time T second, that is 60 second, its concentration is changed to be Y, and by putting the value and we are able to taking the log, we are able to calculate the rate constant of the equation. So this problem is given in your book. I have not taken the numerical data. I have solved it by the concept, by using the formula, how we apply the formula to solve such type of problem. Now we take another example, how we calculate that there is some problem to plotting the graph. The value of rate constant, this is now clear all the things. This is a important topic of this chapter. So many problems are based in this mathematical expressions. So you see, now we have the formula, this Kt is equal to by 2.303 and this is log R naught and R. So what is R naught? This is the initial concentration of the reactant. I always remind you, this R naught is the initial concentration of the reactant. And what is the R? Concentration after the lapse of certain time. So you reminded. Now we have the two. Suppose it suppose we have to plot the graph. This is log R naught by R versus T. So again you apply the concept y is equal to mx plus c. So this axis is suppose it is y and this t is in x axis. So we plot a graph and you set the equation as per your convenience. So this is log R naught by R and this is equal to, this is Kt by 2.303 and here there is no intercept, so will be 0. So what will happen? Our aim to plot the graph between this and this. So these are the function, this and the versus this is time. This is versus time. So this graph is like this, log R naught by R, and this is the curve will go like this. This is the y-axis and this is the x-axis. This is the concept to plot the graph on the basis of the that is y is equal to mxc, equation of a straight line. Equation of a straight line. A straight line. So what will be the slope here if asked somewhere? Slope k is equal to 2.303. This will be the slope. Now for the first order reaction, the value of k can also be calculated graphically. The value, that is the value of k can also be calculated graphically. How we calculate it? Let me take the graph. This is kt by 2.303 is equal to log R naught minus log R. This one. So what is this is the variable and this t is the variable because the concentration changes with respect to time. So we consider as the axis log R is here is equal to minus kt by 2.303 and this is plus log R naught. So again the concept. So this is y is equal to mx plus c, equation of a straight line. Our variables are this and the t. So if a graph is plotted between log R versus time, because the slope is negative, that's why the curve will come downward. So the value, this is this, and this will give the intercept. This is called the intercept. So what is the slope of this? That is minus k by 2.303. So this k is equal to, therefore k is equal to minus slope into 2.303. So we are able to calculate the value of the rate constant if the slope is given in the questions. So there is a relation for the first order reactions. This is for first order reaction. For first order reaction. This is if the slope is given for first order reaction, we put the value of the slope and multiply with this factor, we are able to calculate the value of the rate constant either by this one and this one. Suppose now another problem. So we take this is the first graph and this is the that was the another graph. Now there is another graph. Then we come in the another topic. Now there is some problem to discuss. Suppose we take a first order reaction takes place and it completed 99 time taken to complete. A first order reaction takes place. A first order reaction. First order reaction. Sorry, question is written in such a way, in symbolic form. Time required to complete a first order reaction 99.9% is twice the time required for 90% completion. This is for first order. This is question. You have to prove a first order reaction takes place and the time required for its 99.9% completion is twice the time required for 90% completion. Is that clear? So we take it equation. This is how we'll solve it. There are so many such type of problem in your book. Log, this is R naught and this is R. Is it clear? Now you see time required for this one, that is T for 99.9% completion. So we write here T for our convenience 2.303 but a K, and this one is log, and here R is the initial percent, that is 100, and out of 100 it takes a time T to complete 99.9%. So this is the, if 100, then 100 minus 99.9, this is percent, this one, this is 0.1. Is it clear? This is 0.1, right? Now time required T for, this is equation 1, so it can be solved easily. That comes to be how much? That is 10.3. Now we take the time for 90% completion. We calculate it, please. So T for 90%. Now this is 2.303 and this is K, and log is equal to 100. Now 90% complete, 100 minus 90, that is equal to 10. So it comes to be 2.303 by K and log, and this is 90, 10 and 10. This is 10. This is 10. So this is this one, 90%. So you solve this equation. When you solve it, so what will we get? This is equation 2, and log 10 is equal to 1. So what will be the value here if you will solve it in another? This equation may be written as 1. This is or in easiest way 2.3, and this is equal to K and log 3 log 10. 2 log 10, 100 minus 90, that is 0.0. So 3 log 10. Somewhere you will do the calculation, that is 100, and 100 minus 99.1, that is 0.1, and this is 3 log 10 comes to be 2 log 10. That is comes to be what? 100 minus 90, that is 100, 99.1, this is solved. And by putting this 2 by 1, that is equation 2 by 1, that is 1 by 2, and you check that you will get the answer for this type of problem using the value on this equation. So if there is some calculation error, you check it, but the basis is the same. Now we take another the equation for this one, another problem based on it. So such type of problem can be solved by using this equation of the first order reactions. Now suppose we take another example. Suppose a graph R is equal to K, and this is 1. Now what is another graph we have to plot? Half-life. What is half-life? Already defined. Half-life is the time required in which the concentration of the reactant reduced to half its initial amount. If T is equal to T half, then R is equal to R naught by 2. So from equation half-life for first order, heading should written half-life for first order. From equation K is equal to 2.303 by T log R naught by R, this one. So we write here K is equal to 2.303 by T half, and this is log R naught by 2. So we have the equation that is point 2.303 by t half and log 2. This will cancel out. So the value, if you will put the value of 2.303 and this is t half and 0.3010, then k comes t half comes to be, that is 0.693 by k. So this is the half-life for the first order reactions. So problem based on that half-life is given, then you are able to calculate the k, and by knowing the value of k, we are able to calculate the time, or if the initial and the concentration at a given time is known. If time is given and initial is given, then we are able to calculate the value of R. So this is the fundamental thing. So we have the another equation, this is now, and we come here t half is equal to 0.693 by k. So we have to plot a graph. Plot a graph. This is probably the third graph and this is the fourth graph. So here we plot a graph between rate and versus concentration. So this is equation y is equal to mx plus c. So the equation will pass through the origin because r is equal to k and this is a, and y is equal to mx plus c. Here intercept is 0. That's why the curve will pass through the origin. This is, now if there is a concentration t half and we take the concentration, because it is a constant, a curve is obtained like this way. So this is the graphical representation for this, from this equation for the first order reaction, for the half-life, and earlier plot is earlier plot for the log R and versus T. So the problem based on graph we can plot by that equation. So what is the use of half-life? Use of half-life. Half-life problem is given, suppose a radioactive element whose half-life is given this much, and the initial concentration or initial amount is given, time is also given. You are able to, you have been asked to calculate the R. We can easily calculate with the help of this equation. So we have the another collection of equation, that is T half. That is T half. That is T half. T half for first order, this is 0.693 by K. This is the equation. Sorry. Now, we have another graph. Suppose AB type. This is another equation for gaseous molecule, for gases. For gas. So it will dissociate to give A and B gas. There are so many problems based on it. So I finally write the equation, then I will prove it. 2.303 by T log P naught, or initial pressure, or this is 2 P naught and pressure at a given time. If you will see like this type, suppose SO2 Cl2 decompose to give SO2 and the Cl2, and pressure is at a certain time is given, you have been asked to calculate the rate constant. By using that formula directly, we are able to calculate the value of the rate constant, right? Now how it is, and another, and so how it is derived, you see, let A, and this is a gas, and B is also a gas, so this one. Now here the initial pressure when T is 0, that is P naught. Now at time T seconds, so here the AB molecule will going to, its pressure decreases, and the 1 mole of A and 1 mole of B will fall. So its pressure will increases. Let it is P and it is P. So it will decrease from a pressure, that is this P. This is called the pressure at a time T second, right? So the pressure, total pressure, total pressure, total pressure after time T second. So this is according to the partial pressure, this is the sum, that is equal to Pt बराबर P0 minus P plus P and plus P. So this P and P will cancel. So we get what? So this is very important. Some students get confused how we are able to solve this problem. If you will have the concept, then you can easily solve the problem. So need to develop the concept yourself, right? So this Pt is equal to P naught plus P. So we can calculate P. This value is to be find out first. This is P is equal to Pt. P is equal to Pt minus P naught. P is equal to Pt minus P naught. Is it clear? No. This is the P. Now, the pressure of AB after time T, pressure of AB, that is gas, after time T, its pressure reduced, and by what figure? That is P naught minus P. Is it clear? Suppose it is there SOCl2, SO2Cl2, write here SO2Cl2, and you calculate this one. So we put the value of P here, P naught minus. This P is written as Pt and minus P naught. So what will be here? That is P naught minus and Pt and plus P naught. So this will comes to be 2P naught minus Pt. So this is now this P naught is directly proportional to that R naught is directly proportional to P naught, and R is directly proportional to, that is likewise. So R is that is time T, that is equal to P naught minus P. Now this P naught minus P is written as 2P naught minus Pt. That's why we put in the equation, that is the equation for 2.303 by T and log R naught by R. This one. So what we write here in the state of this, that is equal to, so we need some space. So we can write here like this, 2.303, and what is R naught? R naught is P naught, and what is R? R is twice P naught minus Pt. So we put here twice P naught minus Pt, and we put all the values. Initial pressure, suppose the time is given, that is 0 second, its pressure is 5 atmosphere, and calculate the rate constant at a time 100 second. And 100 second the pressure of that gas is given, suppose 0.65. Is it clear? So we put that pressure at a given time. Initial pressure is given and your time is given 100 second. You are easily calculate the rate constant of this equation. How we will solve it? Let you see. So how we will derive this formula? By putting this value, we get this 1. From this it can be obtained. So suppose a gas initial pressure is in that table, it is like that in your book, it is given. This is the pressure in atmosphere, here time, serial number, this is pressure in atmosphere, time in second, 0.5, and this is here 100 second, and this is that is 6.5, and it is said that to calculate the rate constant for this equation for 100 seconds. What we will do it? So time is given 100 seconds. Initial pressure P naught is given, and this is twice P naught. That is the initial pressure, and we deduce the formula. That's why directly we use that equation how to solve the process type of problem. Any problem is given like AB gas, A gas, B gas, or some in wording form is given. No need to write the equation. You see that the gaseous molecules are given. Then you will apply this concept to solve the problem. So I hope that you are able to solve the problem. There are so many problems in your exercise problem. That is probably 18, 19. These are the problems based on this equation. One exercise problem given in your book that is based on another formula. So by this we can solve it. So another formula comes how? Suppose a molecule AB is given. It is a gas. It decomposed to give twice a gas, and this is B gas. So you will mark here, this is twice AB and this is AB. So what will be the formula we used for that? We write here 2.303 by T and log, and this is P naught, and this is 3 P naught minus 2 PT. Again I will prove you how this formula will come. And we put the value here. P naught is the initial pressure and PT is the pressure at a given time. You know it, this notation, initial pressure, and this PT, that is pressure at a given time, So you will note it. Now, how will solve it? You see again in the same way. So 2AB, that is twice A, plus B, let at time t0, this is P naught, this is 0, t second, that is P naught. So there is two molecule disappears, 2A is formed, these are gas, condition is gas, always gas, and this 2 moles is formed, its pressure is increased by 2P, and it is 1, that is 1P. So the pressure reduced here is 2P due to this one. So total pressure after time t second, that is t second, P naught minus 2P plus 2P plus P. Again, this will cancel. P naught plus P, that is P total. Is it clear? So we find the pressure. P is equal to, that P is equal to PT minus P naught. Now, so pressure of AB after time t, that is equal to what? This one. So pressure of AB after time t, that is equal to, it becomes its pressure reduced because the molecules are formed on the right product side, minus 2P. So you put the value of P, this is P naught minus 2, and what is the value of P? That is equal to P naught minus, and this is P naught. So it comes to be P naught minus 2PT and minus plus 2P naught. So it comes to be 3P naught minus 2PT. Right. So this is the pressure at time t, and this is the pressure at that time t. So we have the equation. We write here. We have the equation. So we have the equation, that is similarly K is equal to 2.303 by T log, and this is R naught. Basic concept is the first order reaction, and we are using the first order reaction for the gaseous reactions, this one. So here R naught is directly proportional to P naught, or R naught we can write for R naught that is equal to that is P naught or directly proportional, whatever we write, and this is that is R that is directly proportional to that is P naught minus 2P, and this value comes to be that is 3P naught minus 2PT. So for this, what we write here, or we can write this value, and for this we can write this value. Is it clear? Or we, if you have confusion, then we write like this. We can write this one. That is, this is called the, because R naught is the initial concentration and P naught is the initial pressure. That's why we write here. So we putting the value 2.303 by T and log. What is here? P naught, and this is 3P naught minus 2PT. So this is the equation for the gaseous molecule. So we have the rate constant for the first order reaction, and all the problems given in your book will be based on this concept. I hope that you are able to solve the problem now. You try yourself. This is, I have given the hints for the problem also for your rate constant for first order reaction. If the different concentration are given and different time interval, use this equation. Now half-life is given, then you calculate the K from this, and then whatever asking the question, if it is asked that calculate the concentration after a given time, this is, then we are able to calculate the R by taking the anti-log. Now if the gaseous molecule is given, and if type, this type AB, A and B, directly use this formula, and how it is derived and what we have considered, I have already explained it. If the molecule like 2AB, not AB, here is 2AB, twice A plus B, then we use this formula. So the problem based on this, based on this, based on this, based on this, based on this. So our aim to clarify the concept, and now it is your duty to solve the problems. So this is the topic I want to conclude today's topic. Now I will take one more class regarding the solve of the numericals based on the Arrhenius equation. There are 4 or 5 problems are given in your book based on the that is Arrhenius equation. So I will do in the next class. I hope sure that you will follow my instructions, and then you will go through the book and the lecture and try to solve the numerical problem. If you have any problem, then you can tell in the next class. I will be able to solve it. Okay, thanks a lot for your lessons listening. Thank you.